Okay, so last time we looked at the history of the atmosphere. Now we're going to look at the history of learning about pressure and studying pressure. So we're going to start way back. We're going to go way back to Galileo. So the first guy that we're going to look at is Galileo, and he developed a suction pump. And it's basically like if you took a syringe and you put it into some water and you pulled water up the syringe by pulling the plunger up. And I typically will demo that in class. He used the air to draw water up a column just like a syringe. And he found that there's a limit to how high that water could be raised, and it's about 10 meters. And he figured that, well, look at my suction pump. It's being run by horses. I mean, this is a long time ago, 1600s. Probably not the best equipment. It's not the most technologically advanced tool. So maybe it's probably because the pump's not actually pumping hard enough. It's not strong enough to pull that water up. So 10 meters is about 30 feet or so. But that 10 meter actually became a pretty important number. So a guy by the name of Evangelista Torchelli studied under Galileo, and what he did was he determined that it wasn't Galileo's pump that was the problem, it was actually the pressure of the atmosphere was not strong enough to push the water up the tube, up the column. So what he did was he took a tube, filled it with mercury, and he inverted it in a pan of mercury at sea level. And the height of the mercury in that tube is equal to what he figured was our atmospheric pressure of on the mercury in the pan. And he basically, in doing so, he made the first barometer. He also, in doing so, he found that air has mass. It exerts pressure. And he also believed that the top of the column, if there's any space in there, that would have been a pure vacuum, not a vacuum cleaner, a vacuum in terms of the absence of air. So if you think about, this is basically what he had built. He had this tube, and he filled it up with mercury. Now, if the mercury fell, which it did, it shows it's lower here, that's not airspace in here. That would be a vacuum because there was no air. There's no way for air to get trapped or to get caught in there or to get sucked in there because this is all sealed. So now, what's holding this mercury at this level? Well, it's actually the pressure of the air that's pushing on the mercury surrounding this tube is actually holding that mercury up because that mercury wants to fall down. Gravity wants it to fall down. But it can't because the mercury outside has pressure on it, so it's not allowing that mercury to fall. And he actually found that the height of the mercury at sea level, the highest it could go was 760 millimeters. That comes back to our units for standard pressure, which is standard pressure was 760 mmHgs, or millimeters of mercury. Now, the reason why we don't use water, if you go back to Galileo's suction pump, you could pull water up 10 meters. So Torchelli actually found that it wasn't Galileo's pump that was the problem, it was the atmosphere is not strong enough to push. So if we were to use water, if Torchelli used water in this instead of mercury, he would need a tube that's 10 meters tall, or basically 33 feet or so tall for it to actually show different pressures. That obviously would be too big, so we use mercury instead. The other thing I want you to think about is this is actually how a straw works. If you have a straw, here's a straw, here's a glass with some beverage in it, and we always think that we're sucking up the straw, we're sucking the liquid up, but we're actually not. When you suck on the top of the straw, you create a vacuum here. That's a U. You're creating a low pressure in your mouth and at the top of the straw. And there's a high pressure, so you got low pressure here. I'm going to put low pressure here. And you're getting high pressure pushing on the liquid outside. So that liquid is actually being pushed up the straw by the atmosphere, the difference in pressure. It's really not you're sucking up the liquid, the atmosphere is pushing up the liquid. And that's exactly what's going on in our pan of mercury as well. There's a video that I'll post in the lesson as well from Veritasium where he actually shows how that works, and they try to suck liquid up as high as they can in a straw. So watch that one, and he explains it fairly well. So that brings us, and it's in the link in the notes as well right there. The next one is Otto von Graf, and he basically took the idea of the water pump, basically, the air, and he created an air pump. So basically, he created a vacuum pump. And he used that pump to create a vacuum in two hemispheres. So basically, he pumped the air out of this sphere here. And what he found was that vacuum was so strong. This was, by the way, this is a recreation of his experiment. That's not the actual one. This didn't happen way back then. The vacuum was so strong that a team of 16 horses could not pull those hemispheres apart. And that actually shows us how strong our atmosphere actually is pushing. And it also pushes in all directions. So inside this hemisphere, he had low pressure, and outside the atmosphere, pressure is high. So that atmospheric pressure is what's holding those two hemispheres together. So basically, he found that vacuums don't suck. It's actually the atmosphere that pushes. So then we go to a guy by the name of Blaise Pascal, and he took Torchelli's barometer, went up and down a mountain, and he found that as he went up the mountain, the column of mercury would actually fall down, and as he went down the mountain, the column of mercury would rise. And he's basically saying or showing that the pressure of the atmosphere was changing with his altitude. And because of this, we later named the metric unit of pressure the Pascal after him. Then we talk about a guy named Christian Huygens. He's the guy, I'll just do that. He's the guy that invented that manometer. I showed you one in class of a YouTube. And basically, a barometer measures the pressure of the atmosphere. A manometer measures the pressure of a gas by comparing it to the atmosphere. And then we come up to John Dalton. And Dalton, to me, this is kind of a thank you, Captain Obvious moment. But he said that in a mixture of gases, the total pressure is the sum of all the pressures of each gas. Basically, this is called the law of partial pressures. So if I put air in my tire, I'm putting nitrogen, oxygen, carbon dioxide, and argon, let's say. Well, the total pressure of the tire is the pressure of the nitrogen, oxygen, carbon dioxide, and argon, if you sum them all up. So it's the law of partial pressures. Every gas exerts its own pressure, and when you put them all together, it totals. Kind of makes sense. But then came along a guy by the name of Joseph Louis Gay-Lussac, and he came up with the law of combining volumes. And basically what he said is that gases react in volumetric proportions. In other words, if we're talking about water, 2 volumes of hydrogen combine with 1 volume of oxygen to make 2 volumes of water. Basically, H2O, 2 volumes of hydrogen, 1 volume of oxygen. And he did this experiment where he ran electricity through water, and you can actually, one side will make hydrogen bubbles, so that's hydrogen gas, and one side will make oxygen bubbles, oxygen gas. But what you'll notice is the hydrogen balloon will be 2 times bigger than the oxygen balloon 1 time. So it would be half as big. So you're actually getting twice as much hydrogen as you are oxygen because of the ratio of H's to O's. So that's called the law of combining volumes. And then along comes a guy by the name of Amadeo Avogadro, and he used some of those experiments to determine that the pressure of a container, pressure that's in the container, is directly proportional to how many things are in the container. To me, again, this kind of makes sense. The more stuff you put in the container, the more air you put in your tire, the more pressure you have. The more air you blow into a balloon, the more pressure in the balloon. So that kind of makes sense. Now, that brings us to the units. So now we should probably define what pressure actually is. So in physics, we talk a lot about forces, and forces are a push or a pull. Now, with pressure, though, pressure is a force spread over an area. So I want you to make sure that we understand that it's not just the force, it's the force spread on an area. So I can push my entire body. So let's say I step on 1 nail. All right, so I have my foot and I step on 1 nail. That nail is going to go through my foot. But if I step on a bed of nails, or lay down on a bed of nails and put my whole body weight on it, it's the same amount of force, because I weigh the same, but that force is spread out over a larger area. So it doesn't hurt and it doesn't go through you as much. So it's less pressure. Think about wearing high heels versus flat shoes. The pressure or the weight of your body is transferred throughout your foot rather than just onto the front of the balls of your feet. So the pressure observed by our atmosphere is called atmospheric pressure. We've been talking about that a little bit. So pressure is a force per unit area. And in physics, they talk about forces being called newtons. And that's a kilogram meter per second squared. So what does that mean? Well, a newton is if you can lift 1 kilogram, 1 meter high in 1 second, that's a newton of force, which is not that much. It's like lifting just over 2 pounds, 1 meter high in a second. Pretty easy to do. So newton's not a lot of force. And if you do that over a square meter, that's a pascal. So a pascal is really a small unit of pressure. So now we want to talk about standard pressure, because pressure does change wherever you go. So we have to have a standard. And we consider sea level to be the pressure of 1 full atmosphere. So that's where the unit atmosphere comes from, because 1 atmosphere would be the pressure at sea level. So at sea level, you'll have the entire weight of a column of air above your head. That's 1 atmosphere of pressure. Now, everybody says there's less oxygen as you go higher in altitude, and it's not necessarily that there's less oxygen. The percentage is about the same. It's just that there's less everything. The air is more dense the lower you go because gravity is just wanting to pull it down, right? It has mass. It has whatever. Even though the particles move in every direction, air does have mass. So gravity will affect it. So your air is thicker and more dense at the surface of the Earth and thinner at altitude. So if you go up to the top of a mountain, there's less air above you. So like if you're standing up here on the top of Everest, there's less atmosphere. And if you're standing down here, there's a lot more atmosphere above you. So there's a lot more weight, more pressure. So that brings us to the units. The first unit we're going to look at is something called a kilopascal, which is basically 1,000 pascals. If you remember your metric system, kilo means 1,000. So if we talk about a kilometer, a kilometer, that's 1,000 meters. A kilogram is 1,000 grams. A kilopascal is 1,000 pascals. And that's a Newton per square meter. So you're putting a Newton of force on an area that's about a meter squared in size. That is exactly a meter squared in size. And that's called a pascal. That's about like if you were to hold a postage stamp in your hand, that's about the pressure of 1 pascal. It's really, really small. It's super nothing. So we often talk in terms of kilopascals because if we're talking about our atmosphere, which is 101.3 kilopascals, that's standard pressure. If we were to just use the units pascals, because they're so small, it would be 101,300 pascals. That's a lot. So we use kilo instead of pascal. Just like if I wanted to measure the distance from here to Texas, I wouldn't measure it in meters, I would measure it in kilometers or kilometers. Millimeters of mercury. So where this unit comes from is using the Mercury Barometer because it measures the height of the mercury. So it turns out that at sea level, mercury was able to be pushed up the column 760 millimeters, or about 76 centimeters. So that's a lot less than the 10 meters of water, because mercury is a lot heavier. So these are our 3 major units for pressure and that we've seen in the previous part of the course. These are what we call standard pressure. Now there's a couple other units that you may see, you may come across. One is called the torr. It's named after Torchelli. It's meant to be the same idea as millimeters of mercury, but its definition has changed. For all intents and purposes, in our course, we're going to say that 1 torr is 1 millimeter of mercury. So standard pressure in torrs is 760 torrs. It's fairly close. It's not exact, but it's close enough. We don't need to get into too much detail. The unit actually has changed many times. And another one that you may see is more for meteorologists, and they're using a unit called a bar. They usually talk about it in bars or millibars. Basically, you can think, and it's not exact, but you can think of 1 bar as being the same as 1 atmosphere. So really, our 3 major units are these ones, and you could interchange torrs here, and you can interchange atmospheres here. It's the same idea. The conversions are fairly close, so we can just say it's about the same. All right, so we did a little bit of looking how to convert a unit, but let's review just to make sure we understand. So if I want to convert 1.5 atmospheres, so I'll start off with my 1.5 atmospheres, and we want to convert that to, let's start off with kilopascals. We'll just do that one first. So if we want to convert to kilopascals, we got to set up a ratio that gets rid of atmospheres and leaves us with kilopascals. So we know how those two things are related. We know that every time you have 1 atmosphere, you have 101.3 kilopascals. So I'm going to take 101.3 times 1.5, and I get 151.95, and the units that will remain are kPa. Now, if we want to convert the 1.5 atmospheres to, let's do millimeters of mercury now. Well, let's get rid of atmospheres. So they go on the bottom, mmHgs on the top. And we know that 1 atmosphere is the same as 760 mmHgs. So 1.5 times 760 is 1,140, and the units that will remain are mmHgs. Now, if I want to convert to pascals, it's a little bit different. Well, not really, it's the same idea. But now that we have kilopascals here, what I'm going to do is I'm going to multiply by a ratio to get rid of kilopascals and get pascals. So I'm going to put kPa here and PA here. Well, we know that 1 kilopascal is the same as 1,000 pascals. Kilopascal, 1,000 pascals. You have 1 kilopascal, you have 1,000 pascals. So now, kilopascals cancel. 151.95 times 1,000. So you're talking it would be 151,950 pascals. So once you have kilopascals, then you can go to pascals. All right, that's unit conversions. Now, a couple things about measuring pressure. So both units, both of these things, manometers and barometers, they kind of sound a lot alike. They're both used to measure pressure of a gas, but one measures the pressure of gas in a container, and one measures the pressure of the atmosphere. A manometer measures the pressure of the gas in the container. That's that U-tube manometer that we saw in the last unit, where we were measuring vapor pressure. Now, a barometer measures the pressure of our atmosphere, and that is just like Torchelli's barometer. This is what a weatherman's looking at, because they want to know the pressure of the atmosphere and how it changes. That actually dictates how our weather changes. And this is kind of what it would look like set on a wall. So the atmosphere is pushing on this pan of mercury here, and if the mercury goes up the tube, then the pressure is going up. The atmosphere is pushing harder. If the mercury falls down, then the pressure is going lower. So we can measure how high. So there's a couple different types of barometers. Not that we really need to get into it too in depth, but there's something called an aneroid barometer. It's kind of more of a mechanical barometer. It's using an expandable drum here that kind of expands and contracts based on the pressure. Pretty easy to read. You might have. I remember my grandpa having a humidity barometer and a thermometer kind of set in his house, and it was kind of like the old school weather station, and you could look at it and see what the temperature was, the pressure was, and the humidity, and that's basically what these things are. It's not the greatest in terms of accuracy, but it works, and it's pretty easy to read the pressure off of. There's another barometer. It disappeared on here, I think. You should have, mercury barometer we just did on the last one. Yeah, so that's the mercury barometer, and they're a lot more accurate. So that's the aneroid barometer. Now, feeling pressure, we feel pressure in lots of different ways. Not pure pressure, it's a different kind of pressure, but you can feel pressure with your ears popping on a plane, or difficulty breathing when you're at a high altitude. Divers, if they dive deep and surface too quickly, they get the bends. They basically actually have gases bubbling in their blood, and it can actually kill you. Pressure on your body when you swim underwater, you can feel that pressure building up the deeper you go. You can feel it on your ears and your head, and especially if you have a cold, you can definitely feel it on your sinuses. So when you're diving, the weight changes, and the pressure, the changes in pressure are amplified because of the weight of the atmosphere and the weight of the water. So not only do you have the weight of the atmosphere above you, you also have the weight of water above you. So now in fresh water, divers actually tend to feel less pressure against their body than in salt water. And why might that be? Well, it's very simple. Salt water has salt in it, so it's heavier. So salt water adds more weight, and it creates more pressure. Because remember, pressure is just force. Weight is a force. So you put that weight on your body, and it feels a little bit more forceful. So a diver can actually dive deeper in fresh water than in salt water, because the salt water is a little bit heavier. Basically, if you're diving in salt water, you go 33 feet down, and that's like an atmosphere. So if you're 33 feet underwater, you have about 2 atmospheres above you, because you have an atmosphere of water and then the atmosphere of air above that. If you go 66 feet down, now you've got about 3 atmospheres of pressure on your body. In fresh water, you can go a little bit deeper before you hit the same pressure. And that is the units on vapor pressure, or sorry, on gas pressure.